Hello all, welcome to this series of tutorials in which we will be understanding and learning how to code using Pytorch. The series of these tutorials, the aim is to come up with the codes starting from creating the basic tensors till running CNNs and RNNs and extending it further to the idea of transformers. Now, let's start taking simple steps and then let's start understanding the need of PyTorch. PyTorch is one of the libraries that is helping us, enabling us to write codes for machine learning applications. Now, there are multiple such uh, packages like PyTorch, TensorFlow, and MXNext. But PyTorch is more famous now because it is more Python-like, and then it is easy and intuitive for us to work with. It resembles Python in most of its working and in its syntax, now so that someone who is very well equipped with the programming in Python will not see much of a difference, saying that okay, no, this is something new that is happening. Okay, so now we all by now know that the major uh, difference, okay, now that is needed for machine learning is the huge scale of data, and then the operation that is repetitively performed is matrix multiplications. So now CPU is not suitable for this. We have GPUs, which are specialized units, graphical processing units, now which are designed to perform these matrix multiplication parallelly, so that with smaller cores, so that effectively we are able to go ahead and perform this operation in a smaller amount of time. So you might have, all of you know, a company called Nvidia now, which on the day of this recording is having the huge stock around their valuation is around $5 trillion. Okay, now, that is the level in which, and everybody needs it. Okay, so now there is a very famous joke that goes like, when everybody is digging, now you start selling shovels. Okay, now it is like that. When whoever wants to do this machine learning, so the basic need is this GPUs, and then these GPUs, so you want to perform any operations on these accelerators. Okay, now we need PyTorch like packages which enables us to do. The first component now which is there here is what is known as tensors. Now Now, these tensors are similar to the NumPy's uh, ND arrays. So you would have used NumPy's ND arrays. Now it is similar to that. Now, but the difference is now tensors are equipped with functionalities now in which the operations can be done on hardware accelerators, and then a very interesting and the important workhorse of machine learning now, which is the idea of back propagation, now can be done using what is known as automatic differentiation, autograd, now which is there, which we shall look it up sometime in our due time. Okay, so that is there. Okay, this enables us to do. So now, how do you create these tensors and how do we work with them? So let's start with that. Okay, now we need the package torch. This is the base package that is there, and then so we will see how to create these tensors first from a regular list which we have, and then a NumPy array that we have, and then how do you interchange between them. Now we will see. Therefore, for that reason, I'll import NumPy also. So now what we will have is, now let's say that I have a data x, okay, now which is 1 comma 2 comma 3 comma 4, okay, now then you can know the type of this. Print type of x. Now we can see that this will be a list, okay. So now how do you convert this list which is there into a tensor? Now x tensor equals to torch dot tensor of x. Here you can print x tensor, print type of this x tensor which is there. Now you can see that this is not a list anymore. You have converted this into a tensor, okay, and then even the type is indicating the same thing. Okay, so now you have a tensor which you have obtained from the list. Now similarly, we can obtain it from the NumPy array as well. So now what I'll do is, so I'll first convert this list which is there to NumPy. Now how do I do it? Now np dot array of x. Okay, so now you can print this xnp and then type of this. Okay, this is a NumPy array that we have the xnp. Now how do you convert it from NumPy array to tensor? Okay, x tensor from NumPy. Okay, now this is now torch dot from NumPy. Okay, so you just have this. Okay, so now if you have the data that you have in the form of a list, that also you can convert, or if you have the data in the form of your NumPy array, that also you can convert. Now, by now all of us know that any data that we look into, either it's a matrix or a sequence, now that is nothing but vectors. It's in some RD. Okay, it's a vector in RD. Now this is how we create tensors. Now there are now sometimes we might need to have now tensors now which is of certain properties, which is of certain shape, now which is having same elements. Okay, something like that. If we want to do that, now let's create what is known as a tensor, now wherein which all the elements are one, and it is resembling the properties of x which is there. Okay, the tensor x which is there. Now how do I do it? Torch dot ones like. Okay, now you have x tensor, you can print this x once. Okay, this is of the same size as that of the, or same shape that as the x tensor which you have, but everything is one. Now if you don't want all ones, if you want a random tensor which is of the same shape of the x data, now we can always create it. Now torch dot rand like. Okay, now x tensor I want it to be in float values, so that I use torch dot float to indicate that I want it to be. Now this is a random tensor now which is of all the elements are floating values, and then this is of the shape x tensor. Okay, so I assume that these are clear. Now this is, you're saying that you're giving a data and then you're saying that like this you create. Now I don't give the data, I just give you the shape. Is it also possible? Now yes, it is possible. You can provide the shape. Now let's say that the shape is 2 comma 3. Okay, just need to include the other comma here. Now you can have rand tensor, okay, random tensor, now which is torch dot rand of shape, okay. So and then you can have all ones, okay. One's tensor is torch dot ones of shape, or you can have all zeros, okay. Zeros tensor is torch dot zeros shape, okay. Now we can print all of these, okay. Print use formatting, random tensor once, and then this zero tensor, there has to be a, yeah, okay. Now you can see this is a random tensor which is of shape 2 cross 3 and all ones and all zeros. Now we can obtain tensors like this. Okay. Now this you can give it for any RD you can obtain. You can for any grid that you want to do. You can provide the shape and then obtain it for that particular grid structure. Now that's totally fine. I'm just showing you as a simple example for 2 cross 3. Okay, so now what are the attributes of tensors? Let's look at them. Attributes of tensors. Okay, now couple of important attributes of tensors are what are the data type of the tensor, and on what device it is there, and what is the data type, device, and then what is the shape. Okay, shape of the tensor. Now these are some of the very key attributes that we might be checking again and again whenever the need arises. Okay, so now let's create a tensor. Okay, so now let's say that I have z tensor equals torch dot rand. I can just provide 3 comma 4 the shape here itself. So now I can print these properties, these attributes, shape of the tensor, shape of tensor, data type of this tensor. Okay, so and then on what device it is there. How do we do it? If now device tensor is no, on what device it is there, that you can use obtain it by using dot shape dot d type and dot device. Okay, now the shape is 3 comma 4. All these are 32-bit floating values, and then currently it is on CPU. Now, because I haven't enabled the GPU access yet, we will, when we create the model structures, all these MLPs and structures, at that time I will show you how to port it onto a GPU. Now I have just used the CPU, so it is showing that it is on the CPU. Okay, now, these are some of the very important attributes, and then please remember, whenever you want to perform an operation on a tensor, now both the operands or the involved operands now should be on the same device. Okay, now either it is CPU or GPU. No, it has to be on the same device, otherwise it is not possible to perform the operations. Okay, so now now since we have, let's look at operations of operations on tensors. See, there are a lot of operations now, including arithmetic operations, linear algebra operations, matrix manipulation operations. There are a lot of options. Now, there is a rough estimate, there is more than thousands of operations that are there. Now, all these operations can run on CPU as well as on the CUDA device. Now, that's what you should remember sir saying about CUDA. Okay, so on all these accelerator device, now they can run. Okay, now by default, whenever a tensor is being created, now it is, as I told, it will be created on the CPU. Now, then you have to explicitly move it to the GPU for its working. Okay, only when the CUDA device is available. Now let's look at some of the very bare minimum operations now that now we can do. Okay. Now these operations, see, now for all practical purposes, whatever operations that you can do on NumPy ND arrays now can be done on tensors. Okay, so now let's look at some of the indexing and slicing. Those are the basic operations that we can think of. Now let's do them. Okay, so now I have already have this Z tensor. I'll just use the same, which is of size 3 cross 4. Now let me print it so that we can understand the output. Print Z tensor. Okay, this is the thing. Now let's say that I want to access the first row. Now print. Now I want to access the first row. Now how do I get it? See, things are evolved. It knows the basic kinds of operations that first row, now first column, and then you want to access the, let's say that last column. Okay, or you want to manipulate uh, the columns here. Okay, the first, so this is actually the column with index 1, which is the second column actually. Now let's do it. Now here you can see that this is the first row. Okay, now and then the first column 0.60244. This is the first column. Now you're able to access it. The last column is this, and then you have modified column with this is the index 1. I have modified it to 0 like this. These are the basic operations, indexing and slicing operations that we are comfortable in performing NumPy array. And those things can be performed now here also. And one other operation that might be interesting is this concatenation of tensors. Okay, so now let's do that. Let's say that see concat. Now, whenever I say concat, now whether are you doing as per the rows or as per the columns? Okay. So now let's do that. Now let's first do as per the columns. Okay. Now you have this Z tensor that you are placing next to one another. Now because of which you are concatenating as per the columns. Now to indicate that you have to specify dimension as 1. Now that is when you are doing as per the columns. Now, as you can see here, now this is a 3 cross 4. Now it has become now the 3 cross 12. Okay, the 4 repeated thrice. Okay, it has become 12. Okay, now this is along the columns you have concatenated. Now similarly along the row also you can concatenate. Now you concatenate along the rows. And now these things have become you say in one line it will understand what is the next operation, that the next word prediction that we shall be seeing sometime in our course. See, you can see that in work. This is along the rows. Now you can see the concatenation. Okay, now this is regarding the concatenation operation. Now let's look at the crux now, which is the arithmetic operations. Now these are matrices, and then now we know that the basic operations that we want to actually perform are matrix multiplication and then element wise multiplication. Now these are the basic operations that we want to perform. Okay, now let's look at them. Now let's do matrix multiplication. Okay, now see, I am assuming that all of you know the basic rule of matrix multiplication. Okay, so I'm assuming that you know it, and then I'm proceeding with that. Now, let's say that I have y1. I'm multiplying that with z tensor. Now, this is the matrix multiplication operation symbol that is there, and then dot t. Now it is transpose. Now, what is the shape of this Z tensor? Now this is a 3 cross 4, correct? So now you have this, which is a 3 cross 4. that you are performing a matrix multiplication with the transpose of it, now which will become 4 cross 3. Now we all know that whenever these two are matching, you can perform. Now the outcome now will be a matrix now which is 3 cross 3. Okay. Now these sanity checks needs to be done whenever you are going ahead and performing the operations on matrices. Okay. Now the sanity check of the matching of the shapes needs to be looked into. Okay. So now what are the different ways? This is one way of doing it. The second way is now you use the tensor and then you call a method now which is dot matmul, and then you pass the second tensor there. Okay. Now this is the another way of doing it. And the third way of doing it is you create a placeholder now, which is it should not be of type y1. Now it has it has to be of type y1, because y1 is the product. So it is you create a placeholder for this, and then you pass the both the operands. Okay, so z tensor, and then where do you store the output? The output is stored in this y3. Okay. Now torch.matmul, this you can use, or you can directly use the matrix multiplication method, which is there with this instance of tensor which is there, or you can use this at operator which is there. These are the three different methods that you can use, and then all of these three should yield to the same result for sure, but these are the three different methods that you can use. Okay, this is matrix multiplication. All of them are yielding 3 cross 3 things. And the other thing that we have is element wise multiplication. See, element wise multiplication is it's something like this. Now, now, all of you are comfortable with the Hadamard product, which is preferably working with uh, vectors. Now, let's say that I have two matrices, and then they have to be of the same shape. Okay, so now we represent this matrix, element-wise matrix, element-wise multiplication by this asterisk. Let's say that 2, 2, 2, 2. Okay, now the outcome will be you take this and you multiply by this. Okay, this is 2, similarly 4, 6, and 8. This is you take this element, multiply with this element, you get this. Okay, this is element-wise multiplication. This is another operation which is needed. Now remember, now whenever in CNNs, I assume that all of you have seen the CNNs. Now you have to perform this element-wise multiplication, then finally add. No, okay. Remember that operation, something similar to that. Okay. So now let's look at this element-wise multiplication. Okay. So let's say that I have okay, T1 equals this, or you can use dot mul. Okay, so or you can use so you create T3 which is of the shape of T1, and then similar to the torch dot matmul, you can use this, and then you can print all of them together. Okay, now this is the element wise multiplication which is there. Okay. Now these are some of the operations, and other uh, single element tensors is like, for example, let's take this z tensor dot sum. Okay, so let's see this output and then see here. Now this is dot sum is you're adding all the contents of the z tensor. Now dot item, now what it will do is, now see, now this is a tensor. Now as you can see that this is a tensor. Okay, and Let's print this AGG and then type of this AGG. This is a tensor. Okay, torch tensor. Now, dot item is used to port it onto the CPU. It is trying to convert it into a Python numerical value. Okay, now, this will be a tensor. Now, it's a 1 cross 1 tensor, so that you are converting into a Python value. So you can perform this sum. So now I presume that you can look into the convolution operation now as combination of these two things. Now, similarly, you can add a scalar. Okay, so now that is also possible. Now that is, I can say that Z tensor dot add. Let's say that I want to add 3. Okay, then print Z tensor. Now you have added 3 to each of the elements. Okay, now these are some of the basic operations that you can think of, and then you can work in using these tensors. Okay, now I assume that these are clear. So now the next thing that we should look into is, okay, now these are fine. Now the next important question that arises is, okay, now these are tensors. Now, all my input will be tensors. Now from where do I get the input? Okay, now you need for any supervised learning task, now you should be aware by now that now we need features and then labels and targets. Okay, features, labels, or targets. You actually need them. Okay, now how do you obtain these data? Okay, uh, that might be in the form of an image or in whatever format it is. Now, how do you get them? Okay, now this is for that we have libraries uh, like data sets and data loaders. Now we will use them. See, whenever we are dealing with data, no, now some of the academically available data sets are there in the Pytorch library itself. So we can go to Google and then you can check for so Pytorch data sets. If you go to this Torch Vision data sets, sometimes it takes time to open. Now all the basic academically needed data sets, okay, are present there, like MNIST. There is one more data set called as fashion MNIST, which is also a 10 class problem. Okay, and then you have Caltech, flowers. Now during our discussion we shall be using these things. Okay, now you can actually obtain those data sets directly without any much of hassles. But most of the commercial applications, the data may not be publicly available. Okay, now whenever data is not publicly available, now we need to actually load these data now physically. Okay, now these are two different. One is academically available data is readily available. Okay, now the second one is now commercially needed data. Now it is for any given company now needs to be loaded right, uh, explicitly. Now, how do we do this? Is the next question. Okay. So now, first, let's look at the commercially available data. So now we will be taking here the famous uh, MNIST dataset. Okay. We'll be looking at the MNIST dataset. Okay. Now we need to import torch, that is like the vanilla thing that is needed. Okay, and then we need from torch dot utils dot data import dataset from torch vision import datasets to tensor matplotlib. Okay, Now, these are the things that are needed. So now let's do this. Now these standard academically compatible data sets, they have their training and test split now, which is actually done. Okay, you don't need to actually perform the train and test split. Okay. Now, if it is not, no, we have to randomly perform a train and test split. But for MNIST, the train and test split is there. Now, if we need validation set to take care of hyperparameter tuning, now normally the prescribed way is, now you take some from the training data set. Okay, that is the prescribed way. Okay, now let's look at the training. Okay, training data. Now, where is this? Now, it is there in datasets.mnist. Now, it is there. Before, I think it got loaded. Now, you can see that these are the different image classification datasets. Now, here 101 means there are 101 classes. Okay, here 256 means 256 classes. 10, 100. You can. This is fashion MNIST, food 101. So, there are a lot of these datasets that are there. Now, this is for what do you call classification and detection and segmentation. Also, you have optical flow. Now, you have a lot of different tasks for which the data sets are readily available in the repository, which we can take and start working. Okay, fine. So, we will not be going into that. Okay, these are the different things that are available. But first, let's load the MNIST. Okay, so now you can directly load it from this data sets. That's the reason why we use Torch Vision. Okay, now I need this MNIST. Okay, so now this now if you want to work on this, now that has to be physically present on your device. Now in this case, Google Colab, it has to be present in your current working environment. Now where it will be? Now it will be downloaded, if it is not there, to this folder from the current running directory data. Okay, and train is equal to true indicate that you're downloading the training data. As I told you, the train and test split is there. Now download is equal to true. That means that in the given path, if the data is not there, you download it. And then what do? You convert it into tensor. Now why we have to convert it into tensor? Now because these are numpy images that you have to convert it to tensor. Now these are known as transformations. Okay, so now see, you have your features as well as your labels. Okay, now here I'm only giving the feature transformations. Now, sometimes you might even need to do a target transformation also. Okay, now just keep in mind now that, okay, in most of our cases we might not be needing it, but that is also there. You might need to transform the targets as well. But as of now, we are just converting the NumPy images, the NumPy arrays which are there, into tensors. Now that is the reason why I'm using this to tensor. Now, this is the transformation that I'm applying. Okay. Now this is for the training data, and similarly for the test. Okay. Test data. Okay. It itself will take. This is now you have to so look out for that in this data from the current working directory, and then train is false. Now that means that you are actually downloading or you are dealing with the test data. Download is equal to true. That means that in the given path, if it is not there, you download it and then transform. Now whatever data is there, you transform it. Now as you can see, this is my current directory in which I'm running on the Colab. Now I don't have any data. Now once I run it, okay, it will take some time to load. Okay, you can see here the data is there. MNIST raw. Okay, you will see all this. This is in some. Okay, it's not opening. But anyhow, you have this files ready for you to work with them. Okay. Now the data uh, is ready. Okay. Now this is when we have comfortably now having the data set in the Pytorch repository. Now, what if that is not the case? Okay. Now, what if that is not the case? Now, then we have to actually build a custom data set. Okay. Now, now what is needed for this custom data set is one thing, a file wherein which you have the path to the image and then the corresponding label. Okay, that is one thing, and then a folder in which all these images are there. Okay, even if they are what do you call spread across. Now in the file you should have the proper namings done. Okay, so now let's do it. Now let's create a custom data set. I'll just show you how to create a custom image data set class. Okay, so and then if you have any custom data set, you can use a similar approach and then you can do it. And one other approach that people actually have is now they will segregate the data. There is folder 1, folder 2 for each of these different classes. Now then loading will be even much more simpler. Now I'll leave it as a small task for all of you. If the data is like that, now how do you do it? Now here, what is my assumption is there is a folder in which every image is there, and then there is an annotation file in which the relative path and then the label is there. Now how do you work in those cases is the criteria in which I'll be taking. Okay, but if it is neatly arranged in cases like, okay, each class is segregated in folders, then how do you do it? Now we use what is known as image folder. I'll leave it up to you with this much of clue. Okay, so now to create this, now import OS. Now you need to go around the directories for which you need this, and then since we are dealing with an annotation file which is a CSV file, now we need pandas. You're using pandas as PD, and then from torchvision.io, now you have to read this. Now import decode image. See, I'm assuming that we are working with images. Okay, the same idea can be extended whenever you are dealing with sequences also. But remember, whenever you are dealing with sequences, what should be the length that should be taken is the one that needs to be considered. Okay, I'll not be going ahead with that. Now we are as of now taking the images. Okay, so now class custom image dataset, and it has to be inheriting the data set which is there, and then let's have the init method. Okay, and this now we should have self annotation file image directory, uh, transform none, and target. Now this is okay. Now annotation file is the file that I told you. It's a CSV file. Now in which CSV or TSV, anything file. Now in which you have the relative paths and then the labels that are there, and image directory is the absolute path till that point. Okay, now annotation path is from that file, it is relative, where are the existing. Now image directory should be the absolute path from the root or whatever you have till that point. Now transform is on the features. Now what are the feature transformations that you want to do it on features, and target transformation is what are the features that what are the transformations that you want to do it on target. Okay, now this needs to be considered. Now then self dot image labels now equals pd dot read CSV. I'm assuming that this is a CSV. If not, please make the changes. Now image directory is this, self dot transform equal to transform, and you get the target transform. And then now we need to have this length. Okay, Now, why is this needed? Now you remember that, so we have to cut them into batches. Now for that we should have this len exactly the same name, but depending on the kind of file or the kind of structure that you have, the return value might change. Okay, but underscore underscore len underscore underscore now has to be retained the way the name it is. Okay, so now you should have this length, and then we should have the get item. Now the get item is where in which every time now you will be getting one image, one features, and then its corresponding target or the label. Okay, so one at a time. So now image path, first you should get the absolute path to a given image. Now how do you get it? You have the absolute path till the directory, and then in the annotation file you have from the directory to the file, to the file. So now what you have to do, you have to join them. Okay, so now how do I do it? Os dot path dot join. Okay, so image directory, and then that is the first column. Okay, and then you decode its path and get the image. Okay, now whatever id that you are getting, now that row, zeroth column. So you'll have two columns in your csv. The first column will be your relative path, and the second column will be your annotation. So you're obtaining the whatever id that you are getting, the zeroth column, the value in the zeroth column of it. So now, and then what is the label? The label is the first column, correct? So the label which is there, and then now if there are any transforms, now you will apply. If self dot transform, you will apply. Okay, now if you have any target transformations, okay, that on the label you will apply the target transformation, and then you return image and label. Okay, and please remember this len and then get item, the names has to be retained now as it is. Now it's not like now you can modify them. Okay, now this is how you create a custom ImageNet. So now since I have this data, now let's print one of these data and see, okay, how it looks like. Let's do it here itself. So now I can get train features, train label. Okay. Now this is 12828. Now the MNEST image size is 28 cross 28. So that is fine. It's a torch, it's a tensor. Now actually my aim is to print it. Okay, train features, comma, train labels. Now I use the iterators. So next of IT year of training data. Okay, so and then the image that we are considering will be the zeroth one, and squeeze, and then the label, and then you plot it, plt.image show, and you get it. What happened? Int object is not subscriptable. Okay. Okay, let's do this rather than working with this. Let me see whether I'm able to plot this first. Okay, this is the uh, image that we have. This is of 5. Okay, you can off the grid and do those things. So I'll not be going ahead with that. So this is how you can plot a single image and convince yourself that, okay, now these are the images. Okay, so now at this point we stop this section of tutorial. So in the next section of this PyTorch explorations, now we will be looking at how do you create a neural network. Okay, we'll be first creating an MLP, and then we'll be looking at the automatic differentiation and optimizations. Okay. Thank you all. I hope you enjoyed this session. We'll meet in the next tutorials looking at a very important idea of building the neural network. Thank you.